Let's talk about sinusoidal functions. An example of a sinusoidal function is something like this. F of x equals sine of x. This is something we can actually graph, right? If you decide to make a table of values with x and y, and your x values have to be in degrees, right? Because you're taking sine of those values. So we'll use 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. That should be good. That is going to represent one cycle, because if you think of degrees, 360 degrees means you've gone around the circle once. If you continue to increase, you're going around the circle a second time. So this is what we would call one cycle. So for your y values, or I guess I should really call that f of x, right? F of x. What's f at 0? Well, f at 0 is sine of 0. Well, what's sine of 0? Well, if you recall, if you think of our angles on the plane like this, we always start from here and we work our way around in that direction. So 0 degrees means we're still on that arm, right? We haven't moved up yet. And what's sine of that? Well, sine is all about your y direction, right? If you're having an angle up here, sine represents the height of that triangle. Well, if you're just on the arm like this, you're at 0 still, right? Your height is 0. So sine of 0 is 0. Now what about 90? Well, 90 implies that you've gone all the way to here, right? Well, what's the height when you're here? Well, in this situation, we're assuming that the length of the arm going around this circle is simply 1, right? We have a radius of 1 when we do this. So sine of 90 degrees is going to equal 1. If you do 180 degrees, that means you come all the way down to here, right? What's sine of that? Well, the height here is 0. You haven't gone up or down, right? So the sine there is 0. If you come 270 degrees, that means you're down here, right? Well, what's the height at this point? Well, you're going to be down at -1, right? That's your height. And when you come back up to 360, you're back where you started. So you're back with a sine value of 0, right? Because you're just right on the x-axis. And so with this data, we can go ahead and we can plot what this function looks like. So we have a maximum value of 1, a minimum value of -1, right? At 0, you're at 0. At 90, so I'll say this is 90, you're at 1. At 180, you're at 0. At 270, you're at -1. And then here at 360, you're back to 0. This makes, if you connect the dots, a nice curve. This is what we call a sine wave. That looks pretty good. And what's nice about this is it continues in both directions forever. So if you continue to the right, you'll continue to have the sine wave as you go to the right forever. And it also continues into the negative, so it'll go this way, right? Just continuing forever to the left as well. So what I've drawn here is what we would call one cycle of the sine wave, right? Or one cycle of the function. Likewise, we can do this for cos, right? I could say f of x equals cos of x. And you could make a table of values all the same, just like this. And you could use 0, 90 degrees, 180 degrees, 270 degrees, 360 degrees, so just every 90 degrees, right? These are the main points. And you'd figure out, okay, what's cos of all of these? Well, if you think of that plane again, and you start, you're here, that's 0 degrees. Cos of 0? Well, what's your cos value here? Well, you're 1 to the right, right? Remember, your radius is 1, so your f of x will be equal to 1. Okay, what about 90 degrees? 90 degrees, you're up here at the top. Well, your cos value for there is going to be 0 because you're right on the y-axis. You're not moved to the left or to the right. You're at 0. Remember, cos is all about your x value. 180 degrees, you're over here. The cos of 180 is going to be -1 because we're 1 to the left. When you're down here, the cos value is going to be 0 because you're not going to the left or right, you're right in the middle. You're at x equals 0. So 270 is 0. go to 360, you're back where you started, at 1. So with this information, we can graph the function f of x equals cos of x. You have a maximum value of 1, a minimum value of -1. At 0, you're up at 1, so you start at the top. At 90, you're at 0. At 180, you're at -1. At 270, you're back at 0. And at 360, you're up at 1. And then you can connect these dots together to make a nice curve. This is what you would call a cosine wave. Just like that. And just like the sine wave, this continues forever to the right, like that, and forever to the left, like this. You know, it just goes on and on and on. So what we've drawn here is one cycle of the f of x equals cos x function. And so one other thing you could say is that one cycle of this function is equal to 360 degrees, or in other words, one period is equal to 360 degrees, because that's the length here, the duration that it takes to show one complete cycle, to end up where you started. Okay, let's move on. Let's talk a little bit more about this cycle or period business. So if you have a function that goes like this, right, something like that, and it goes to 360 degrees, so this is just y equals sine x, right? Let's say you have another function that does something like that. It goes just as high as the wider function, and it goes just as low, right? They both go up to 1 and down to -1, just as an example. They're both starting at 0. The only difference is the wider one goes to 360, and this shorter one only goes to 180. Okay? What you could say is that the period, or the cycle, of the longer function is 360 degrees, but the period, or the cycle, of the shorter function here is 180 degrees. Because that is the distance it takes to go one full cycle, right? You start here, and you end up at the same position you started at, right? That's a cycle. You do it again, you get another cycle. Keep going and keep repeating. So that's what the cycle is all about, or the period. Now there's another characteristic of these functions that we should talk about, and it's called the amplitude. The amplitude refers to the distance from the center to the top, or the center to the bottom of these functions. So for example, you have a cos function like this, and we'll say the period is normal, right? 360 degrees. And the middle of this thing is at 0, that's where it's all based around. It has a maximum value of 1 and a minimum value of -1. What would the amplitude of this be? Well, the amplitude, like I said, is the distance from the middle to the top, or the middle to the bottom. So whether you take a look at this graph and say, oh, this is a distance of 1, that's a distance of 1, therefore the amplitude is equal to 1, that's perfectly acceptable. But another way to calculate this would be to take the total distance from the top to the bottom and divide it by 2. Because after all, the amplitude is half of the total height, right? From the very top to the very bottom, that's a distance of 2, right? From 1 to -1, that's 2. Half of that is your amplitude. So you could say that the amplitude is equal to your maximum point minus your minimum point divided by 2. In this case, 1 minus -1 divided by 2, which is 2 divided by 2, which is 1. So you can get the same answer just by looking at your graph. But this is the way to show your work. Now, let's talk about another characteristic. We also have what we call the axis, or the midline. You might hear it referred to as different things. In this case, the axis, or the midline, is referring to that imaginary horizontal line going through the middle of your graph. So an example like this, right, where that's just a regular graph, right, that's at 1, that's at -1, you know, the period's 360 degrees, just like we've been looking at. What's the axis? Well, the middle is at 0, right? So the axis, or the equation of the axis, would be y equals 0. That is the equation of the axis, because that's the equation of the line going through the middle of your graph. One way that you can find this is by saying, oh, it's the average of the maximum and minimum values, right? So the equation of the axis is equal to, you could say 1 plus -1 divided by 2. Well, 1 plus negative 1 is 0. 0 divided by 2, and that's 0, right? So y equals 0, just like we said. So in general, you could say that the equation of the axis is equal to, let me write out a nice equation for this, y equals maximum plus the minimum divided by 2. This is the equation of the axis or the equation of the midline, whatever you wish to call it. It looks very similar to the last equation, right? The equation for finding amplitude, except amplitude we're subtracting, right? But nonetheless, if you don't want to memorize these equations, you can usually find where these things are located or what the values are just by looking at your graph, right? Just look for the number halfway between your maximum and minimum. Halfway between 1 and negative 1, of course, is 0. Let's look at some transformations now, because these functions deal with transformations the same way that other functions do, although they have their own unique twist on what we call those transformations. So let's say I have f of x, and I'm just going to write out the most general form. A sine k x minus d plus c. Very similar to every other type of function that we've seen. In the past, we said A represents a vertical stretch or compression, right? Hopefully you remember that. But in this case, we have a special name for A, and that is our amplitude. So if A is just 1, the amplitude is 1. If A is another number, then we have a different amplitude, right? Then you have the K value in here. K value in the past we would call a horizontal stretch or compression, right? But now that we're dealing with these sinusoidal functions, we can refer to this as the frequency. Or in other words, the number of cycles in 360 degrees. In other words, if I want to even write this a different way, I could say that the period of the function, so the length of that cycle, is equal to 360 degrees divided by k. So we'll do some examples on this later, and hopefully it'll make more sense once you see the numbers in action. Your d value, that used to be a horizontal shift to the left or right. So I'll write that out, horizontal shift or translation, perhaps. Left or right, and remember when it's on the inside here, because it's minus d, if you see a minus number here, a negative number, that means we're going to the right, and if it's plus a number, we're going to the left. But now we have a special name for this. It's called a phase shift. It means the same thing though, right? These all mean the same thing, but they just have their own special names now. And for C, we used to call this a shift up or down, but now it also gets its own special name. This represents the equation of the midline, just like we talked about earlier, or the axis if you want to call it the axis. So all these terms still have the same impact on the function like they would with any other type of function, but they have their own special names. So let's go ahead and we'll do an example. Let's say I have f of x equals 2 sine 1/2 x minus 180 degrees plus 4. Okay, what do we do? Well, let's start off with our plane like this. Okay, and we'll start with y equals sine x, our parent function. Y equals sine of x. What does that look like? Well, that's just a basic sine function, right? It goes like this. It goes up to a height of 1, down to negative 1, right? This here is 360 degrees, right? This here is 180, right? There's, 90, there's 270. Nothing too exciting about it, right? Just like the basic function. Now let's add one of our stretches, right? Because if you recall, we're supposed to add our stretches and compressions and reflections even before we do our shifts, right? That goes back to when we were transforming other types of functions. So let's do that next. Okay, so let's say we have y equals 2 sine x. Well, that 2 is your amplitude. So the new amplitude here is going to be 2. So it goes up to 2, back down, down to negative 2, then back up. So it just looks like a stretched out version of the original function, right? It goes up to 2, down to negative 2, just like that. Okay, now let's introduce that 1/2, because that's your horizontal stretch or compression, or at least that's what we used to call it, right? So y equals 2 sine 1/2 x, just like that. Now remember, that 1/2, that's your k value. And remember what we said, the period is equal to 360 degrees divided by k. In this case, k is 1/2. Well, 360 divided by 1/2 is 720 degrees. So the new period is 720 degrees. So this is being stretched horizontally, right? So instead of going to 360, it's going to be twice as long. It's going to go to 720 degrees. So this green graph here is going to have to be stretched out horizontally. So the middle point that was at 180 is now going to be at 360. So it's going to be here, it's going to touch here, it's going to touch here, and its maximum is going to move from 90 to 180, just like that, and its minimum is going to move right here, halfway between 360 and 270, which should be 540 degrees. So if you want to label that, you can. And these are all going to be connected just like this. You try to do it neatly, right? Do your best to make a nice curve, just like that. Okay, next we can do our phase shift, right? Our minus 180 degrees. So when you subtract 180, that means we're moving to the right 180 degrees, right? So y equals 2 sine 1/2 x minus 180 degrees. So we're moving everything to the right 180 degrees. That means that this starting point is going to move to the right 180. So it's going to be, instead of at 0, 0, it's going to be right here. That's the new starting point. This maximum point that was at 180 is going to move to the right 180 to 360. Right? So everything's moving to the right. That point that was at 360 is going to move over to the right by 180 degrees to 540, just like that. This point at the bottom is going to move over to here, and this point here is going to move to the right 180 as well, right to there, and that's going to be at, well, 180 plus 720, that's going to be 900 degrees. That's where it ends. And that's just going to be down here because, well, hopefully you can tell by the pattern, right? So now we connect these dots together. Again, try to do a nice, neat job. Make it a nice curve. Mine is not the best, but it's okay, right? Just do your best. Okay, and then finally, we want to add this plus 4 on the end. That is changing the equation of your midline, or in other words, we're moving up 4 units. So the equation of the midline used to be here at 0, right? That's where the center of your line was, the center of your function, I should say. That's going to move up to 4. So 4 is going to be here, right? And you can draw a dotted line there, if that helps. Now remember, because the amplitude was 2, you go down 2 and up 2. So we're going to draw this purple graph here, but everything's going to move up 4. So that negative 2 is going to move up to 2. That point right here at 0 is going to move up to 4. This point that's at the maximum at 2 is going to move up 4 units up here all the way to 6. Okay? This point here is going to be right there. This point down there is going to be there at a height of 2. And this point at 0 is going to move up to 4. So every point is just moving up 4 units. Okay? So it's the same as this purple graph, it's just everything's moved up 4. Then you connect those dots together, just like this. And that's not too bad, right? So that's one way to do it. Another way to do it, if you don't want to use the transformations the way I just did, is you could make a table of values, right? You could plug in a number of angles like 0, 90, 180, and so on, right? 270, 360, a whole bunch of angles. Make a nice table of values, and you'll see this shape emerge, and then you'll be able to graph it. So that's another method that you could use. But at the end of the day, this is f of x equals 2 sine 1/2 x minus 180 degrees plus 4, this one here. Okay, let's move on to another example. Okay, this one we should be able to do pretty quickly. Let's say we're given a graph. Okay, so we're given this graph, and it looks something like that. Okay, and we can see the minimum value is -1, and the maximum value is 1. And we can also see that it has a period of 360 degrees, right? And so that means that halfway is 180. right? It means that this point here is at 90 degrees, and this point here is at 270 degrees, right? So you have all these key points, of course, and we can also see that it starts down here. That's at 0 degrees, of course. So we know all this information, and now the question is, write an equation to represent this function. Well, how can we do that? Well, if you take a minute and you really take a look at this, you might notice that it looks like the upside down version of cos function, right? Y equals cosine of x. It's just the upside down inverted shape, right? Or in other words, it's been reflected over the x-axis, right? So what we could say is this is y equals negative cos of x, right? Because again, cos of x just looks like this, and this is the upside down version of that. So it's been reflected vertically, so you just put a negative on the front, right? That's one way you could do this. What's cool about these functions, though, is that there's an infinite number of equations you can use to represent these graphs. Another would be if we decided to use sine, right? Now, how can you say this is a sine graph? It doesn't look like a sine graph. A sine graph starts here and then goes up and then comes down and does all this stuff. Well, if you look at this, if you started here and then went up and then came down and then went up, that would kind of look like a sine graph, right? Like this part of it, that looks like a sine graph, right? And so it looks like this could have been a sine graph that moved to the right, right? Normally this point here would be here, but it's been moved to the right. So I can say that an equation that represents this graph is sine x minus, because we're moving to the right, 90 degrees, right? Because 90 degrees is where that point is that used to be at 0. So y equals sine x minus 90 degrees is also equivalent to this. So these two equations are saying the same thing. They're actually equivalent to one another. And this isn't the only way you can shift a function to get this graph, right? Because again, this is a cycle that continues forever. So whether you went 90 to the right or 90 and then another 360 and then another 360 and then another 360 and then another 360, it doesn't matter, right? Because it's just the same shape over and over and over again. So that's why I say there's an infinite amount of ways you can do this, okay? I mean, another way would be if you just said y equals cos of x minus 180 degrees. I say that because usually a cos graph starts at the top. Well, here's your top, right? Normally it starts here, but it's been moved to the right 180 degrees. So you could say it's equal to cos x minus 180. So that's another way that you could represent this. So again, there's an infinite amount of equations you could come up with, and sometimes on a test they'll give you a function like this, and they'll say, hey, come up with 2 equations that represent this, or come up with 3, or come up with an equation using sine, and then come up with an equation using cos. And you'll have to be able to do that. So it's important to know all these transformations, what they do and how they impact the graph.